but just to kind of make sure we're all on the same page, the reason this is so important, and actually I'm going to go ahead and, if you don't mind, take yours. I'm going to take mine and write numbers 1 through, 6 down here. So ion is 1, 2, 3, 4, 5, 6. I'll go ahead and write 1 through 6. So I can refer to this. All these are is basically how you keep matter together. Now, we're kind of familiar with the chemical bonds. These are not chemical bonds. These are actually connecting units, the same, different units. Okay, so these are what we call intermolecular interionic bonds. So I'll be referring to this. Oh, well, before I go on, okay, so if you would, just humor me, where it says ordinary dipole, put the word polar next to that. I'm going to go ahead and put polar molecules. I don't know. Polar molecules. And then skip down to the last one, number 6, and next to that put nonpolar molecules. Let's see. And also at the bottom, if you don't mind, since we're all kind of marking up our thing, there are at least two other names for this different induced dipole. If you would put dispersion forces next to 6, that would be great because it's the same thing. And also put London forces, London forces. That would be great. All right.
So London forces?
London, yeah. So I'm going to be referring to this. So one of the cool things that we talked about was in Chem 1 was physical phase changes. So up here on the slide it says boiling point, or boiling, the word boiling. Just actually it's talking about the phase change from a liquid to a gas. And we know that that's an endothermic process. This is kind of reminding you about the whole Chem 1 thing. And when something goes from a liquid to a gas, are bonds being broken or bonds being formed?
Broken.
Broken, yes. Bonds are being broken, exactly. Okay, so the whole phenomenon of boiling is that's what's going on. And you're probably familiar with, so what temperature does water boil at in Celsius?
100.
100, exactly. Fahrenheit?
Celsius.
212. Yeah, 100 Celsius, 212 Fahrenheit, exactly. Now that's the boiling point temperature of water, but have you ever heard, we'll be talking more about this, if you add salt to water, what happens to its boiling point temperature?
Lowers.
The other way.
Oh.
It elevates, boiling point elevation by adding salt. Okay, so the temperature at which water boils will actually go up. We'll be talking more, actually probably today, I think, get to this idea about the phenomenon of boiling is so cool. Basically something boils, and I'll kind of give you a little precursor to what this is going to look like. When it's vapor pressure, so let me go ahead, and this is my beaker. I'm going to put a liquid in there. We'll go ahead and make it water. I'm going to seal my beaker with a watch glass. I know it doesn't look very sealed, but just kind of bear with me. I'm going to go ahead and I'm going to heat it up. Okay, this is my Bunsen burner. I'm going to heat it up, and it's going to be boiling. Temperature is at least 100 degrees Celsius. If I were to go in here, and these are my little gas particles of water vapor, if I were to here's my pressure gauge. If I were to measure the pressure of those water molecules, they actually would be at atmospheric pressure, which typical atmospheric pressure is 760 millimeters of mercury. So they would be that water vapor would be at 760 millimeters mercury. I'll put PH2O, gas. Okay, so anyway, that's kind of what that is. But let's continue to talk about the phenomenon of boiling. So when something boils, you guys told me it's breaking those intermolecular bonds. So in a way then, the temperature that you're going to get those bonds broken at is an indication of how strong those bonds are. That's it. So boiling point temperature is an indication of how strong those bonds are. Now, I bring to you Exhibit 1, and we only have one exhibit today, okay? This is so cool. So 1 through 6, okay? These are the strongest intermolecular bonds. These are the weakest intermolecular bonds. So bottom line, and you're going to see some things, I know it's weird to think like an ionic compound boiling, but these would be high boilers, just in context of what we're talking about, high boilers, low boilers. High, low. It's a little more complicated than that, but that's kind of what we're after. Okay. So put on your Chem 1 hats, and we talked about these energies associated with something changing its phase. You guys told me we're breaking bonds when something goes from a liquid to a gas, and we are. We call the energy required to make that happen the heat of vaporization. Sometimes we'll add the word latent heat of vaporization. Do you guys remember what's the H stands for? Starts with the letter E. Enthalpy. H is enthalpy. So it's the enthalpy of vaporization. Your H's are enthalpies. So similarly, and you're going to see it on the next slide, I think, if something is I'll hold this thing up here, okay? If something is a high boiling point temperature, it's also a high heat of vaporization. That's all it is. We say they correlate pretty well. They should. Looks like it took out lots of words for that one. You just never know. Okay. Oh, I think I added the arrow thing. I think that's probably what's, okay. Oh, so here's another arrow thing. Okay. So there, at the bottom, again, with regard to increasing latent heat of vaporization, enthalpy of vaporization, the stronger the intermolecular bonds. Notice it could be stronger or it could just be more of those bonds connecting that matter. The more heat you have to pump into it, energy, in order for it to vaporize. It makes sense. I think I added the little arrows because I'm like, well, that's kind of all it is. Okay. So one of your tasks, and we'll be getting a little bit of, actually, this is part 3, right? Part 2, we're going to kind of revisit with part 3 a little bit. So we're going to have to be able to kind of find our way around the different types of intermolecular bonds here too. Okay. So all this is, each green dot represents a substance, and for that substance, we went ahead and came up with its boiling point temperature in Celsius, and for that same substance, we came up with its heat of vaporization. So these are just ordered pairs. And then this talks about the correlation. So if you get a straight line-ish, you're like, they correlate pretty well. They do. Different substances. All right. So I'm going to return to Exhibit 1 here again. Okay. Now, we talked about this is where I have to say this isn't as simple as I said it was. Okay. Down here for non-polar substances, one of the things I talked about in part 2, when Olivia and I had met on Monday, okay, is that something that's non-polar, I just am so excited about this, something that's non-polar actually can become temporarily polar. Okay, we call that, it becomes momentarily polarized. And there's the degree, how easy is it to become polarized, have a temporary region of negatives and positives? That's what we call polarizability. Okay. So, this kind of gets to this one. If you have something that is two things and they are similar weight, okay, that means they're probably similar, potentially similar polarizability. Maybe, maybe not. That might not be what I'm after here. But if they boil at different temperatures, okay, the one that boils at a higher temperature, you've got to have something going on with regard to connecting that material. So you have stronger or more intermolecular bonds than the lower one. The one with the higher boiling point has the higher degree of intermolecular bonding. And I was looking at this in my office, so that was substances with similar molecular weight, okay? So this is new, right? You guys don't have this in your notes. Again, little arrow things are new probably to your notes. So it's possible to have similar weights but have different sizes. I don't know if you similar weights but different sizes. You might just have lighter atoms that are connected together, and it makes the molecule larger. Now this actually does get to polarizability a little bit. The larger you can make that molecule, the more spread out that molecule, the more likely you are to get those regions of temporary positiveness and negativeness, okay? We call it, how do we say, you get that started, positiveness and negativeness, on a nonpolar molecule. You're like, what the heck? Well, just electrons are a little bit more over here where it's negative, less over here where it's partially positive. If you can get that thing going on, then that one can actually, what we say, induce a polarity on a nearby molecule. And actually, I kind of have a video part two that showed that. So the region where it's got electron rich actually will induce an electron poor region on another molecule. So if you go back down to number 6, when it says induced dipole, basically you have an induced dipole, pair of pluses and minuses over here. You have an induced dipole over here, pluses and minuses over here, okay? And then they can go ahead and connect, okay? And those intermolecular bonds are this induced dipole. London forces, dispersion forces, they're all the same thing. So again, I had you guys put, for number 6, I had you put dispersion forces. Okay, cool. Let's see. For substances with the same type of intermolecular bonding, now for types of intermolecular bonding, it's 1 through 6. What type of intermolecular bonding do you have? Okay, the one with that boils at the higher temperature will most likely be the one that weighs more because it's more polarizable. Okay. Do I have an arrow thing? Oh, nope. Now, one of the things I covered in lecture on Monday is that, let's just say you have a pair of polar molecules. Let's take water. Water is very polar, okay? So you have the whole kind of already dipole interaction going on. It's not to say, so let me go ahead and make sure we're on the same page. That actually would be, water's not a good example because that is actually what we call hydrogen bonding, connecting those together. But it could be dipole. Now, those water molecules are also stuck together by this one down here. Even though it's a weaker, okay, all substances generally have this induced dipole going on, even if they are polar. That's where I have to kind of step back a little bit. I had you guys put nonpolar molecules here, but even polar molecules have an induced dipole. Put another way, though, nonpolar molecules do not have dipole.
What did you just say the last thing?
Okay, we can fix this. Okay, so down here, induced dipole, I had you put nonpolar. Go ahead and put polar and nonpolar.
Okay.
Let's do that. And then up here, where I had you put polar molecules, ordinary dipole, put only polar molecules. How's that? Because that's kind of the way life is. So this goes to polarizability, this thing in parentheses. We're going to do an example here in a minute, but basically, if you have a molecule, we're going to see where we have kind of different, they're called isomers, okay? They're different kind of arrangements of the same atoms. You can have the atoms all squished together, and it's hard to polarize something when, okay? Or you can have the you can have the atoms kind of joined together so you have something long. Something that's long and not bunched together is easier to induce a dipole. Okay, so that's where it talks about surface area. All right. Oh, there was an arrow thing. Okay, what we got? Larger the molecule, the more London or dispersion forces. Okay, and I've been using the word this afternoon as when I say more London dispersion forces, that's the more polarizable. You can more likely to polarize, induce a dipole. All right, so now we have some examples. Let's see if we can kind of make sense out of these. Okay, these actually are all nonpolar. That's the heading up here. Nonpolar, monopolar molecules. They might have polar bonds. Like for instance, this has a silicon in the middle, 4 hydrogens extending. Now, each silicon hydrogen bond is polar, but the centers of positives and negatives coincide on the silicon atom. So the molecule is nonpolar. Bottom line, though, is here we have an increase in boiling point temperature. So for increasing the boiling point temperature, it must be getting stronger intermolecular bonds, stronger or more. And lock and step, we have the heat of vaporization. The enthalpy of vaporization is increasing too. Okay. And then what your author has done is go ahead and add together the weight of all those molecules. And notice Br2, even though there's only 2 little bromine atoms there, its molecular weight exceeds that of anything above it. I will go ahead and tell you that sometimes it's hard to just look at these 4 and say, oh, that's the order of increasing boiling point temperature. But we're going to have to try with some obvious problems coming up. These are all polar substances. Not only do we have polar bonds, but the overall molecule is polar. The regions of negatives and positives do not coincide. Again, they are arranged by increasing molecular weight, and that's not an accident. Just to kind of emphasize that we have, again, we have increasing boiling point temperatures and increasing enthalpy of vaporization. Now you'd be like, well, what's the enthalpy of vaporization of ICL? And I don't know. I'm probably going to have to look that up. Okay. All right. I just have some boxes. Now we have a video, and my videos this semester are working thanks to Dr. Snipes. It was Christmas break, and I'm like, you know, I never can get any of my videos working. Like, I know the problem. So this is one that actually I did in part 2, but it's here in part 3, and it's going to talk about analogous compounds. The thing here is we have tellurium. SE stands for
Is that selenium?
selenium. Thank you. Tellurium, selenium, yes, and sulfur. And actually H2O is kind of up there at the upper because we have hydrogen bonding. But let's see what the video says. It should work.
A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
So these molecules, the H2TE, the H2SE, the H2S, those are all polar molecules. So do you guys buy this, that's number 4? That's that type of intermolecular bond, okay? And the reason we see kind of this boiling higher, the H2TE boiling higher than H2S, is because tellurium's a lot larger molecule. Atom. Tellurium's a larger atom. It's a heavier molecule. Okay, so is more polarizable. And then this jump right here, instead of H2O being down here, is because H2O moves up into number 3. It's no longer 4, it's number 3. Okay, and you're going to want to kind of review maybe what we covered in part 2. But let's go ahead and under hydrogen bonding, this is the first semester I've done this. I like doing different things. So under hydrogen bonding, go ahead and do this. Next to it, put an O-H, put a F-H and put a N-H. And just for kicks, since we're doodling, go ahead and put a partial positive over the hydrogens and put a partial negative over the oxygen, fluorine, and nitrogen. So in order for that number 3 to occur, that ordinary, not ordinary, in order for hydrogen bonding to occur, you have to have one of these situations, and we definitely have that before. But notice where number 3 is relative to ordinary dipole.
So it's only with oxygen, fluorine, and nitrogen?
Yep,
Okay.
yep, only. Let's see, I didn't think that was gonna work. I can get back to my show. All right. So this is actually kind of a set, this is 4 sets of analogous compounds. The one we just looked at is the black one at the top, okay? So notice that this is all just boiling point temperature. So we saw that water boils at a higher temperature, the highest temperature. But aside from that, we saw kind of this trend in boiling point temperatures decreasing as we get a lighter molecule, okay? And we see the same thing in the green line and the blue line, okay? If you kind of track what compounds there are. Over here, with the higher boiling point temperature, these are the heavier molecules. But notice that, and we'll talk about this in part 2, I'll go ahead and point it out again. I'd refer you to number 3, the third type of intermolecular bond, okay? This is H2O, this is HF, this is NH3, has this hydrogen bonding going on. That's why, again, the boiling point temperature is so much greater up there. All right. Very good. So, I think it's in Unit 1 in here. We're going to talk a little bit about different types of compounds, especially organic compounds. We're going to give them names. And I think actually we did in Chem 1. Because we talked about the combustion of hydrocarbons. Remember, all hydrocarbons is they contain hydrogen and carbon. But if a hydrocarbon is especially an alkane, okay, they are all singly bonded. This must be coming up in my notes. So these are all alkanes. This first one, what we call the carbon chain, just has 2 carbons. Each carbon has 3 hydrogens around it. Okay. Boiling point, a chilly negative 89 degrees Celsius. So now this is where, if you're like me, I actually have to concentrate. I'm like, okay, so this is about 20 degrees Celsius. So 20 degrees Celsius is definitely warmer than negative 89. So this stuff is definitely a gas. That's kind of how that works. Okay. Propane, we kick in 1 more carbon and add a few hydrogens. So our carbon chain is 3. Okay. And notice then, it's like we talked about before, it's getting bigger, and so you're going to be more likely to have these, number 6, the dispersion forces are going to increase with size. So it's going to boil at a higher temperature. Is it still going to be a gas or a liquid at room temperature? Still a gas, yeah. Then we get to 4 carbons. Now when we get to 4 carbons, I'm going to show you there's different ways that you can arrange that carbon skeleton. But anytime you see, if something is named with an N, that means it's a hot dog. Okay, that means it's just in one straight line. So we have carbon, 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 carbon in this particular arrangement of butane and butane. So if it's that hot dog sort of thing going, you definitely have 2 ends that can become partially positive, partially negative. So would this be a gas or a liquid at 20 degrees Celsius? How many people think it'd be a gas? It'd be a gas, yeah. Because 20 is still warmer than 0. And I think this is my last one up here. Okay, so this is again N-pentane. The A-N-E part of this means that it's all single bonds. This is what we call an alkane. N means it's a hydrogen. Okay, so we basically have 5 carbons, and it's even more likely to get dispersion forces going. What do you think? At 20 degrees Celsius, how many people think this is a gas? How many people think this is a liquid? I do too. Okay. So I just think that I love this, and I was talking to my husband, and he likes this topic too. I just love looking at liquids like that and thinking, oh, you cute little molecules are all stuck together with intermolecular bonds. Okay, but the fact that alkanes are generally nonpolar, okay, they're nonpolar, so you're like, well, what kind of intermolecular bonds we got going on? Well, it's got to be that dispersion forces, the induced dipole. Working hard at it, okay? Do I have another one? All right. Hexane, normal hexane. 69, how many people think this is a gas at 20? How many people think this is a liquid at 20? Me too. Now, it's not, we're going to talk about volatility coming up, and it's not to say it's not volatile. Okay, so those were all alkanes. We had the ethane, the methane, the butane, or the propane, the butane, the pentane, and the hexane. Okay? And they're all nonpolar. You will be on homework drawing structures. I'll say Lewis structures. Kind of use that word loosely. Bless you. Bless you. So let's just draw the last one. 6 carbons. It's normal hexane. So let's see, 4, 5, 6. Okay. And then usually, and we'll talk about different ways of doing this, is I'm just going to put dashes there. And in your own imagination, if you don't mind putting hydrogens on the end of those dashes, that'd be great. We could actually come up with the electronegativity difference between, pick on this one right here. Okay, there is an electronegativity difference, so our carbons are partially negative and partially positive. Okay, but generally speaking, it's a nonpolar molecule. Okay, do I have another? I bet I have another paragraph here. So this last one here, this last bullet, just kind of summarizes the trend we saw with the 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons. As long as they're not bunched up, and we're going to talk about that here in a minute, okay, as long as they're nice and long, they expose ends to go ahead and have, I'll go ahead and put it on here, put that purple up here. Okay, I'm going to erase this because that bond polarity really isn't much. Okay, I'm going to go ahead and make this end temporarily partially negative and temporarily partially positive. And that's an induced. Now, I don't know, induced kind of implies that there was another molecule inside it that kind of made that happen. And there could be. Just basically electron rich over here on the left and electron deficient or poor on the right. Okay, what else we got? So alkanes. Now these are isomers of alkanes. I think I pick on the 5-carbon alkane. Okay, so N-pentane, how are those carbons arranged?
In a line.
In a line, exactly, N-pentane, and this actually is from a previous slide. Its boiling point temperature is pretty high. You guys told me it's a liquid at 20 degrees Celsius. And I have pictures of what these are coming up. Anytime, if you see the word iso, think branched. I'm going to show you what branched is, but basically all it is carbon in the middle, carbon, carbon, carbon. So it's all balled up. It's not long anymore.
And then those H's are all, okay.
Yep, those H's are all like that. And I think it is so cool you can convince yourself if you want to, but there are same number of H's there as there are here. This is I've changed this from hexane into N-butane. 1, 2, 3, 4, 5. Okay. Well, you can see C5H12. So when we ball it up, what happened to the boiling point temperature? It went down, yep.
Still
This is actually
liquid.
what we call balled up. Balled up, this is also called branched. Okay, and that's in the line. Okay.
Barely a liquid, but it's still liquid.
It is still liquid, yeah. Wait a minute, maybe I did that wrong. Oh, drat. This is Neo.
Oh.
I know. How do I get my, this is N, pentane. This is Neo. Drat, oh, how do you get ISO? C, oh, C, C. Yeah. That's ISO, final answer. Sorry, guys. Did you see the difference between these?
ISO is almost a chain, but not quite.
Right. ISO, I had branching, but it's not as balled up as that. So this is N, ISO, Neo, final answer. Okay? This one, I would say
Where's
there's,
the H going on that?
what's that? The hydrogens?
Oh, never mind, I see.
Yep. So we still have 12 hydrogens. That's so cool. So this is the most polarizable. This one we can polarize a little bit. What about this guy? What at 20 degrees Celsius? How many people think it's a gas? Yeah, this would be a gas at 20 degrees Celsius because it's above 10 degrees Celsius. More branching, less induced dipole. And again, I apologize for the synonyms for induced dipole, because there's induced dipole, dispersion forces, London forces, less of that. But that falls under the category of don't blame me. Do I have another one? No, that was it. Okay, good. So there's our N-pentane I drew over here. Now already you see a little bit, do you see how this that I have on the board, you're going to have to be able to find your way around these structures a little bit. Okay, so the CH3, we're going to call those a methyl group. Okay, so basically anytime you see CH3 like that anyway, you're going to have to kind of think this, where these are hydrogens. And each of the CH2s, okay, like that, CH3 on the end. And so here is our iso pentane, which is this one. And then there's our neo. And then I have one more kind of representation that I think is kind of cool to show you. So there's the hot dog one, the spread out one, the one that's in a line. Okay, this is the one that has some branching. ISO has some branching. But then this is the one, the neo, has the most branching. And you're not going to have to memorize the ISO and neo. I would give you those structures. And one last one. Blob, cute little blob that it is. Okay. So each one, this set, these C5H12s, these different isomers of pentane, they're definitely have the same type of intermolecular bonding. I'm hoping you guys would tell me the type of intermolecular bonding is all induced dipole, because alkanes are nonpolar. Okay. So that increasing in boiling points actually has to do with decreasing in, I should say the decreasing in boiling points actually has to do with the decrease in surface area. So if molecular weights are similar, as they would be identical with these C5H12s, boiling points will decrease with increased branching. So for ISO, I'll put some branching. How much branching is there with N-pentane? Trick question? No branching. Very good. So there are some things in chemistry that are kind of visual. This is kind of a visual thing, I think. You can find it kind of looking over your shoulder.
Okay.
Sorry.
Sorry.
Thank you. Okay, that's what I was looking at. The
Oh,
same.
okay.
All righty. Okay, so you could be faced with something like this, where in problems like these, there's no numbers involved. Yay! But you just kind of have to mull it around, mull it over. First off, what you might think, are these polar or nonpolar? How many people think they're polar? How many people think they're nonpolar? Yeah, nonpolar. These are all nonpolar alkane molecules. Let's see. And to me, I kind of break it out into, if I was working this, I would say, well, these two are similar in that they both have, what, 4 carbons, okay? And these two are similar in that they are both no branching. Buy that? Okay. So, let's see. So we'd have to arrange them in order of increasing boiling point. So we want to have the greatest boiling point down here. So highest BP. Highest BP, does that mean strongest bonds or lowest bonds? Strongest bonds, yep. So strong bonds. Okay. And we know strength comes with size and no branching, right? Size and no branching. Size and no branching. Oh, so which one do you think is going to be the highest boiling point temperature? Mm-hmm. No, it's going to be the N-butane. Why? It's bigger and there's no branching. Yep. So this guy is going to be down here. What's going to be the lowest one? So the highest boiling point is going to be the smallest and branching. Well, actually, to me, then's where we start to have an issue. You're like, I'm not sure which of these two will be the lowest. Okay, and there's your answer. Okay. Cheesy. Cheesy alert. So I'm trying to think of, would we have enough information to know that the one with 4 carbons is going to boil at a higher temperature, even though it's got branching? That, I guess, makes sense.
It's because it is essentially, it's larger anyways.
Yeah, I think so too. I think it's got, in addition to this, it's got this.
So the branching isn't enough to offset the extra carbon.
Yeah.
Yes. Yep. The branching is not enough to offset the extra carbon. I agree. So the lowest molecular weight is going to be the one that's going to boil at the lowest temperature, indicating the least amount of intermolecular bonds. Very good. So let's take a quick look, shall we? 2, 4, and 5. I didn't look at these before.
And then we will also have a pre-lab. due
Oh,
for
thanks for, yes, I'll mention that in a minute. Thank you.
Yeah.
2, 4, 5. Well, I've got 4 and 5 here, and there's 2. Or 1 and 2 there. Isn't that weird? Did I assign, what did I assign before? 1 and 2?
Yeah, we already did.
Okay, so it's just 4 and 5. Unless you want to, just because all things considered, if you guys do 1, then I will give you credit for the one that,
For the last three.
Oh,
Yeah.
yeah, 12-1, 12-2. This
Then
one's
if you don't
12
mind
too.
about
Still
that.
turn that in
No,
by
I don't.
the end of today, can't we?
Yes, or you can still turn that in at the end of the day. That's true too. Let's see, let me go back to 4 and 5. 12, 4, and 5. So if you already did it, then this is all that's due, 4 and 5. So arrange these liquids represented in the expected order of increasing normal boiling points. So increasing boiling points, so you're on the right, you're going to have the strongest intermolecular bonds. Okay, highest boiling point. So you don't have to draw Lewis structures, yay! But you need to be able to kind of interpret this general structure. So the blacks are carbons, the reds are oxygens, the whites are your hydrogens, and we have here some yellow, which is sulfur. Together, let's see, did I have more here, or was this the only hints I had? Oh, I went ahead and gave you more hints. Okay, so I put a little asterisk here next to regions of those molecules where you're going to have hydrogen bonding. Okay, what do you think? Hydrogen bonding, will that add strength to the intermolecular bonds or make them weaker? Strength, yeah. So you could kind of think
D
high.
as a bond, D is nothing but carbon and hydrogen.
Yep. Let's see, what else did I have? Is that my? Oh, see, I even had more hints. I did this about a year ago. What does NP stand for?
Non-polar.
Nonpolar. So, do you see where B is nonpolar? Because the centers, those yellow are sulfurs, and they're going to be probably partially. Let's see, what's in the middle? Carbon, sulfur. I bet sulfur's more electronegative. So your yellow regions would be partially negative. Your black in the middle would be partially positive, and the centers coincide. So that goes back to actually part 1 that we talked about in here. That dang thing's nonpolar. And why is D nonpolar? What is D? Starts with letter A. It's an alkane. Yeah. So those are your hints there. So just do your best. So I'd start with bond type, then molecular weight, and go to structure. Let's see.
D is essentially in a straight line, isn't it? Kind of.
Is that the N-alkane?
Yeah.
Yeah. Yeah, that D is the,
It looked like it was,
it looks like it's zigzagging, but it is what we call this straight line up here. One of these substances is a liquid at room temperature. Go maybe 20 degrees for room temperature or so, 20, 22. And the others are gaseous. And then, you have methanol, C3H8N2O2. Let me see what my hints are. Evaluate the compounds for intermolecular bonds. Okay. Did I give you any hints? To me, you don't have to draw the whole Lewis structure, but you kind of have to draw the sticks like you saw before. Don't think through electrons and distribute them and that sort of thing, but just think. In fact, we got a minute. Let me go ahead and draw these kind of so we're all on the same page. I didn't do it before, but I'll do it right now. The first one is CH3COH, so it goes like this. Here's my carbon, here's my OH, and if I do this, you guys know where the other 3 hydrogens are? Yep. Can you hydrogen bond here? I think you can too. Okay, let's see. The next one, let's just go ahead and make that. I think there's only one way you can put 3 carbons, because I don't think you can branch with 3 carbons, do you? I don't think you can. We good with that? That's the C3H8. N2, I think that was the triple bond, wasn't it? I'll go ahead and draw kind of Lewis structure for that, because we did that in Chem 1. That's what the Lewis structure for N2 looks like. How many people think N2 is polar? How many think it's nonpolar? It is nonpolar. So anyway, you know N2 is a gas, like at room temperature, don't you? Okay, just double checking. Let's see. Then the last one is N2O. Did you guys do this Lewis structure? I think you did too. N2O. So we're going to put oxygen in the middle, and I think we're going to put double bond nitrogen, single bond nitrogen. What is that one? Help me out. Electrons would be what? 14 plus 6, 20 electrons. 2, 4, 6. 20 electrons, is that right?
Because the nitrogen has them all the way around
No.
in the.
Nitrogen's a group 5A, sorry. Yeah, that should be 10. So that's 16. Okay, that's better.
Okay.
Okay, so 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. No, because it makes a difference what our structure is.
Is it 2 double bonds?
You think that's it? You have the oxygen, nitrogen,
Yeah, 'cause
like that.
oxygen's
And then,
in-
2 on the end.
and then 2 sets on the ends?
Yep.
Yeah, because oxygen has 6.
Good
so,
job, guys.
Yeah.
So I'm liking that better. Thank you.
Because you'll
So-
swing the ones over.
Good job, guys. So what do you think? What sort of shape do we have going around that from the oxygen? Is it linear, trigonoplane, or tetrahedral? It is linear. So how many people think that this is polar? How many people think this is nonpolar? It is nonpolar. Good job, guys. See if you just take a group test. Thanks. Okay.
Wouldn't we have to know the boiling point of everything to figure out if it's going to be a liquid or not?
No, you can look, you can Google it, but that's not the point.
Gee,
You have to explain it. Explain it. I Googled it. What else do I need to explain?
Just write down the boiling points, here's the boiling points.
No, but you don't need to know the boiling points for sure. All they're saying is if you go with 25, they're basically saying that only one of these, is this right? Yeah. All the others are gases.
And the one with the strongest bond.
Well, that's
Only
what-
one of these is a liquid and all the
Yeah.
others are
well, that's
gases.
what I'm saying. Like, wouldn't we have to know the boiling point of every substance in order to figure out which one would be a liquid?
They're saying the special one, the one that has the highest boiling point is going to be the gas, or be the
Would be
liquid, excuse me, would be liquid, yeah.
Because it would have a higher
Right.
boiling point.
So all you got to do is
25.
find the high, in other words, which one's the highest?
Is it
boiling point
some of
temperature.
it to evaluate which one has the strongest bonds, other than
Yes.
the N2, which is going to be a gas anyway? But if one of those formulas has more bonds between the chemicals, that
More
might-
and stronger, or stronger, both,
Okay.
yep, exactly.
Yep.
And so you're just looking for the one that looks like it's got the strongest bonding.
Whatever has the strongest
And that's gonna be a
bond
liquid.
Like the
will
one
have-
with 2 on either side would be pretty solid, wouldn't it?
No, well, you guys told me non-polar, and if it's non-polar, then it has weak intermolecular bonds, because you're down to this guy.
All
Yep.
right.
I'm liking the hydrogen bond one, actually. You don't need to do your homework for you, but,
I'm teasing.
Yeah. but also you can look it up. But you have to add to that, because you can't Google on your test.